In Chapter 19, we will be looking at a special category of compounds that are described as derivatives of carboxylic acids. Specifically, they will be anhydrides, esters, and amides. So let us look in more details to see what's involved here. So in this presentation, we'll first of all define what we mean by derivatives of carboxylic acids. Next, we will learn the systematic way of naming these derivatives. They are the anhydrides and esters and amides, functional groups that we have seen in earlier chapters. Next, we will look at the synthesis or the preparation of esters, and we'll also look at the reactions of esters. Next, we look at the synthesis of amides and also the reactions of amides. And lastly, we'll conclude by looking at the applications of these reactions discussed here to making a new type of compound called polymers. So we'll define those and give you examples of those. Okay, so the three classes of compounds that will be examined in this chapter are anhydrides, esters, and amides. We've seen those functional groups before. Why are they called derivatives of carboxylic acids? It's shown here. So here's a carboxylic acid, as you can see, the OH. If that reacts with another carboxylic acid, taking off water, that's right here, we get an anhydride. So that's the structure of an anhydride. Here is another carboxylic acid. This is an alcohol. If we take off the water from the reaction between the carboxylic acid and the alcohol, we get an ester. And of course, you will recognize this is the functional group of the ester. Here's an amide. Here's a carboxylic acid. Here's the amine, in this case ammonia. So we subtract or eliminate the water, as shown here. We get an amide, and of course you will recognize the amide functionality is right here. So that's why they're called derivatives. Another definition why they're called derivatives is that if we should take an anhydride and react it with water, we get a carboxylic acid. As we will see, if we take an ester and react it with water going in this direction this time, we get a carboxylic acid. Similarly, we take an amide and react it with water, we get a carboxylic acid. So we'll see those reactions. So that's why they're called derivatives of carboxylic acids. Okay, let's look at anhydrides. We won't spend too much time here, but it's a very important compound in organic chemistry. Anhydride. Here's the structure of an anhydride. It's an oxygen that's bonded to a carbonyl and a carbonyl. Remember, the carbonyl here is really the carbon-oxygen double bond. So it's bonded to both. So that's an anhydride, a special functional group in organic chemistry. In terms of naming it, it's just basically determining what the acid would be and add the word anhydride. We won't get into much details with the naming of anhydrides. We'll get more detailed with the esters and amides. But that's about all we'll say about anhydride. This is the basic structure of anhydrides with the functional group right here, where the carbonyl, two carbonyls are bonded to an oxygen and an alkyl group. they're very reactive compounds in organic chemistry. So they're very useful for synthesis. But let us concentrate on esters. Esters. You will recognize the ester functionality as shown here. A carbon bonded to an oxygen by a double bond, and also that carbon of the carbonyl is bonded to an oxygen which is bonded to an R group. Notice an R group, a carbon containing group. So that's the ester functionality. It may be written in this format, or this format. So you'll have to look carefully to see how it's written so you can identify the ester functionality, because you will have to name it and you'll have to carry out reactions with the ester. So first, let us look at some examples of esters. They are very useful in the flavoring industry and also in the cosmetic industry, because they have a distinct favorable aroma. So here are some for the flavoring industry. Here's the ester functionality, and this ester, if it has this structure here, it has the aroma of banana. Here's another ester. Here's the ester functionality right here, and here's a long chain group bonded to this oxygen and a methyl group bonded to the carbonyl, and that has the aroma of orange. And last one, pineapple. Carbonyl bonded here to this functional group, or this R group back here, and this oxygen is bonded to an ethyl group, and that has the aroma of pineapple. Notice we have the names here, so we'll see how we name these esters using the IUPAC naming system. So let's see how we name them. So here's the ester functionality. Make sure you can identify the ester functionality. It has an R group bonded to the oxygen, and it has here a R group bonded to the carbonyl oxygen group. First, we name this as an alkyl group, and we name this group back here as an alkanoate. So we determine how many carbons are in this group here and name it as an alkanoate. Notice the alkyl comes first and the alkanoate comes last. So here's an example. Here are the two groups. The oxygen has 1, 2, 3. A propyl, 3 carbons, corresponds to propane. So that's a propyl. So that becomes propyl. And the other section is how many carbons are involved in the portion attached to the carbonyl. So it's 1 and 2 carbons, ethane, so it becomes ethanoate. So the name of this molecule here is propyl ethanoate. So that's how we name esters. We have some more examples here. So here is an ester. How do we know it's an ester? Because here's a functional group here for the ester. We identify the group that's bonded to the oxygen, 2 carbons, so this becomes an ethyl. And that comes first. Then we identify how many carbons are bonded to the other portion of the ester, starting with this carbon as 1 and 2. This corresponds to an ethyl again, so it becomes ethanoate. And that's the second portion of that name. Here's another one that's a little more complex. So here we have 3 carbons, propyl, remember 3 corresponds to propane, and here we have 6 carbons, starting with this carbon of the carbonyl. 6 carbons corresponds to hexane, so it becomes an hexanoate. So the name of this molecule here is propyl hexanoate, 2 words. It's possible to have an ester in a cyclic form, and that's known as a lactone. So that's a special name that's given to esters, which is in a ring. So here's the ester functionality. You'll recognize that because this is the carbon to the oxygen double bond and bonded to another oxygen. So here's the R group and here's another R group, but it's in a ring. So these are examples of lactones. The book has more examples. We won't go into the naming of lactones or cyclic ethers, but you should be able to recognize cyclic ethers. As a summary, so we have esters. You should be able to recognize the ester functionality, and remember that there's an OR group that's bonded to the carbonyl. Here's an ester. Here's the OR group that's bonded to the carbonyl. Remember, the carbonyl here is C double bond O, and of course there's an alkyl group. Here's a diester. So here's one ester functionality, and here's another ester functionality. So you should be able to recognize the ester functional group. Here is a cyclic ester, a lactone, and this is a 5-member ring lactone. So you should be able to recognize these functional groups. Let us look at the preparation of esters. How do we make those? We have demonstrated earlier or pointed to the importance of esters in the flavoring industry and of course the pharmaceutical industry and also the cosmetic industry, mostly the cosmetic industry because of the aroma. So how do we make esters? We have discussed this before, the Fischer esterification, which is the reaction of an carboxylic acid with an alcohol. So here's a specific example. Ethanoic acid, here's the acid, with an alcohol, in this case ethanol, and of course the reaction here takes off water. Here's the water over here, and we have this ester functionality. So this is ethyl ethanoate because 1, 2. This is done primarily in the presence of a concentrated acid such as sulfuric acid, and typically we'll have to add here heat to get this reaction to go. So that's called the Fischer. Why Fischer? Because Emil Fischer was a scientist who discovered this reaction for making esters, a very important functional group in organic chemistry. Let's look now at the reactions of esters. Esters are hydrolyzed. Remember, hydrolyze here means hydro means water, and hydrolyze means the reaction with water. So esters react with water. Here's an ester. Here's water. It reacts with water in the presence of a catalyst, sulfuric acid again, to give here the carboxylic acid and the alcohol. So it's the reverse of the Fischer esterification. And of course, as we mentioned earlier, we can use Le Chatelier's principle to drive the equilibrium to the right or to the left. In this case, we can drive the equilibrium to the right by using a large concentration of water to push the equilibrium to the right, so that we have the hydrolysis of the ester. If we needed to make the ester, as in the Fischer synthesis, we just have to take off water or evaporate water so that we have a large concentration of ester made. But here we are concentrating on the reactions of ester. So we add a large concentration of water, and that drives the equilibrium to the right to make the acid, in this case acetic acid. Let's look at another reaction of ester. In this case, it's sodium hydroxide. As you will recall, sodium hydroxide is a strong base. So if we react an ester with a strong base in the presence of water and typically heat again, what we get is the hydrolysis. In this case, it's called saponification. Why saponification? Because the salt that's made here, if this is a long chain, as we've seen before, that's soap. So this process is called the saponification of esters, but it's really the hydrolysis of esters, but it's done in a basic medium. Okay, let us look at another reaction of esters, and this time we're looking at esters with alcohols. So let's see, what is the reaction here? Here's phenol, so here's the OH here. Here's the ester. As we can see from this functional group here. In the presence of an acid, a catalyst, and heat, we have transesterification. So we exchange this alcohol, or this OR, in this case methanol, with this phenol. So this becomes the new ester. So we have gone from one ester, this one is 1, to another ester 2. So that's why it's called trans, because we're just changing the R group here for the OCH3 to form methanol, and we've now introduced this group right here, shown in red. Transesterification. Here's another example. Here's the ester right here. Here's an alcohol. So we'll replace all of this with this group here. Methanol comes off, which is right here, and this group here comes in. This is also an ester, as you can see, but it's a different ester from this ester. So hence transesterification. Let us look at a third reaction with esters, and this is with amines. So esters react with amines to form a new functional group called amides, A-M-I-D-E-S, which we'll look at in more details in the next few slides. But let's look at the reaction. Here's the ester right here, and if we react this with ammonia, in this case, right, this comes off as the alcohol, and the ammonia substitute for that, and that's called an amide. You recognize this group here to be the amide. In this case, it's a primary amide because it just has one group bonded to the nitrogen and 2 hydrogens. So with that in mind, can you predict the product of this reaction of this ester with this primary amine? So here's the amine. All of that is the amine. Here's the ester. This group will come off as the alcohol, and this nitrogen will bond to that carbon to form a new bond here, and this is the amide bond. Oh, by the way, that's a misspelling. So this is the secondary amide. So again, esters react with amines to form amides or amides. Okay, let us look at another functional group here, and this is the amide functional group. Okay, remember we had 3 functional groups which are derivatives of carboxylic acids. This is the third one, the amide. As we can see here, it's a carbonyl right here, bonded to a nitrogen. Notice this is written flipped from what we've seen on the previous slide, but the same bonding must hold. As you can see here, that's a very important bond especially in biology, because it's the bond that hold amino acids together to form peptides. So we have peptides, we have proteins that are amino acids that are bonded together to form peptides, and peptides form proteins. But the main bond is right here, which is the amide bond. Let us see, do a little more details in terms of recognizing the amide bond. Here it is again. The nitrogen bonded to the carbonyl carbon. Primary amide, 2 hydrogens, 1 alkyl group. Secondary amide, one alkyl group, 2 alkyl groups, 1 hydrogen. And of course, a tertiary amide is 1, 2, and 3 alkyl groups bonded to that nitrogen. So you should be able to identify an amide functionality and even take it further to determine if it's a primary amide, a secondary amide, or a tertiary amide. Let us look at the nomenclature of amides. Here's the amide. We'll just concentrate on primary amide. Once you identify the amide functional group, this carbon here gets number 1. And you number in the direction of the longest chain. So 1, 2, 3, 4, or 1, 2, 3, 4, and 5. So you can see this is the correct numbering going here because we have 5 and not here. Once you have 5, you know where that's going. 5 corresponds to pentane. So what do? We change the E of the alkane to amide. So the name becomes alkanamide. So in that case, it becomes pentanamide. And here it is. Once you have the numbering system down, we just have to name the groups that are bonded to each carbon. So hopefully you can see a systematic way of using the IUPAC rules. Remember, the IUPAC here means International Union of Pure and Applied Chemists. These rules were set by these chemists years ago, and it's systematic, it's scientific, so it's just a matter of being consistent with it. So here's a methyl on carbon number 4, and here's an ethyl on carbon number 2. Since ethyl comes before M, it goes first with the appropriate number. Methyl comes next with the appropriate number. Here's another example. 1, 2, 3, 4, and 5. Again, the longest chain. So here is a group sitting on that carbon number 2. Here's a methyl on carbon number 4. And here's a chlorine on carbon number 5. C comes before M or E, and E comes before M, so it's 5 chloro, 2 ethyl, because E comes next, and here's a 2, and 4 methyl, because here's the 4, and pentanamide, Y pentanamide, 5 carbons. And we're using this systematic way of naming amides. Okay, so here's a quick summary. So again, the name is alkanamide. So once you identify how many carbons in the longest chain, just change that alkane to alkanamide, pentane to pentanamide, hexane to hexanamide, etc. And here are some examples. Primary amide, and secondary and tertiary. Let us look now at cyclic amides. It's possible to have a cyclic amide. Here it is. Here's the carbonyl again, and here's the nitrogen. The nitrogen is bonded to a carbon in this case, and the carbon here from the carbonyl is bonded to another carbon, but in a ring. So this is a 4-membered ring here. Don't worry too much about the name. The common name is beta-lactam. But you need to know that a cyclic amide here is known as a lactam. Notice a cyclic ether is known as an lactone, and a cyclic amide is known as a lactam. Here's a 7-membered ring lactam. As you can see here, the lactams are very important functionality in biology. So here's a penicillin, and which of course is known as an antibiotic. Here is the lactam ring. That's a part of it. Here's some other functionalities that you have seen before: carboxylic acid, for example, OH and amine, and so on. So as you can see, a large percentage of the pharmaceuticals are polyfunctional organic molecules. But here, for emphasis, this particular antibiotic contains a lactam functional group. Here's another one. Another antibiotic here is, of course, the lactam functional group. Let us look at how we prepare amides, the synthesis. Again, we have discussed this before, or we have seen this, but if you have an acetic acid, carboxylic acid, in this case acetic acid, reacted with an amine or ammonia in the presence of heat, so this forms first, and then heat, what we have is the amide. So let's see what happens here. The OH here goes with one of these hydrogens to form water. And all of this group here is now bonded to this carbonyl carbon. And here it is. So this is an amide where there's a nitrogen bonded to the carbonyl carbon. Key here is a nitrogen bonded to the carbonyl carbon. That makes it an amide. If it's an oxygen, it's an ester. So you have to be very careful in deciding the functional groups that we've covered here. Let us look now at the reactions of amides. Again, very straightforward. So again, we look at a reaction called the hydrolysis. Again, hydro means water, and of course the reaction of amides with water. So here's the amide. This is a primary amide, butanamide. Why butanamide? 1, 2, 3, 4 carbons, butane. So it's butanamide reacting with water in the presence of a catalyst, acid, and heat. Notice we have to apply heat because the amide bond is a very strong bond. We know that because peptides and proteins are amide bonds, and that's a very stable bond. So we really have to apply lots of heat and a catalyst, H+. When the reaction is done, this comes off as ammonia, and of course the OH here comes right in here to form an carboxylic acid. Notice this is written as an ammonium salt. Why? Because this is an acid, and if we generated ammonia first, the acid will quickly react with that to give an acid-base reaction to give the salt. But the main product here, the main organic product here, is a carboxylic acid. So again, the hydrolysis of an amide gives the carboxylic acid and the ammonium salt. Let us turn our attention now to polymers. So we'll conclude by applying these reactions to a practical example here, or practical examples. So let's first of all define polymers. So polymers are discussed in this section here, and we'll make polymers or show how to synthesize polymers using reactions that we have discussed. Polymers are very important. We've heard the name used in everyday life. Here are some examples. The water bottle that we use every day is made from polymer. The containers, plastic containers, saran wrap, plastic rubber. what's that, topware, even face masks and bags are made from polymers. Polymers are made from small units known as monomers. So we have smaller units known as monomers, and the reactions that we have discussed earlier put together monomers to make polymers. Remember, poly here means many. So it consists of many mers. Mers here means unit. So it's many units, and the units are known as monomers. So let's look at some reactions. Here's a monomer, hexadioic acid. So notice it has a carboxylic acid end here and a carboxylic acid in here. If we react this carboxylic acid end with another monomer, which has an amine. So here's an amine. We have discussed this reaction before. The reaction of a carboxylic acid with an amine gives an amide. And here is the amide bond right here. As you can imagine, here is another carboxylic acid in the same molecule, and here's another amine in the same molecule. So this can react with this, and the reaction keeps going, and that's how we generate a polymer. So in other words, this keeps going, and this keeps going, so we just write N. So we have many of these units in a polymer. The specific reaction here, in terms of reacting this acid with this specific amine, give this polyamide. This polyamide is known as nylon. Nylon 66. It was one of the first synthetic fibers that was synthesized years ago. So it's used to make stockings and different garments. So it's synthetic, and this is what it looks like. Let's look at another example. Here's another example. This one is known as Kevlar. So let's see how it's made. Here's a carboxylic acid again, and here's an amine. You can see it here. So this reaction here, taking off water, as you can see, generates here the amide bond. This amine can react with this, and it keeps going as shown here and going as shown here. So we have N. Typically N is in the hundreds. Sometimes it gets into many hundreds. And so we have a polymer, this type structure, which is made from these two type monomers, make a molecule called a polymer called Kevlar. And as you can see, it's extremely strong and lightweight polymer used, and because of its resistance to heat and corrosion, it's widely used in everyday life. And let us look at another example here. This one here is a monomer which has an ester. Notice this is an ester functionality here, and reacting with an alcohol. Here's an alcohol, but it's a diol. It has two alcohol functionalities. But the first reaction involves the alcohol reacting with an ester to remove methanol. In this case, methanol, because we have just one carbon. So what we form here is an ester. So here we go. Here says a transesterification. And of course, as you can imagine, here's another ester functionality. Here's another OH. So the reaction keeps going, and that's why we have this line here. And N means that we have many of these units, and that's why it's called a polymer. And of course, this is called polyester. And of course, that's another type fabric that's used, and it's used in clothing and used in storage material, depending on the how many mers that are here. How long this polymer chain is gives different properties to these polymers. And I think lastly, we look at another type reaction here. So here is the salt of an alcohol, in this case a phenol. So here's the salt. So reacting this, the phenol with a base gives this salt here. So we have this negative, and here we have a carbonyl carbon, and we have a chlorine that leaves as sodium hydroxide. And as you can imagine, this reacts right here to give us this ester type here. But we have another oxygen here that can react with this to make this leave, or another molecule. So instead of having just an ester here, we have a new functional group here that's called a carbonate. Because it's a carbonyl now bonded to an oxygen and an oxygen. Of course, it becomes a polymer because this continues and this continues, and we have many of these units, of this unit, I should say, that specific unit. And if that becomes a polymer, it becomes a polycarbonate. And polycarbonate, and this one is known as Lexan. Of course, what's done in industry is that these different industries develop different polymers and patent these polymers, and of course that's how they make their profits and their money. So Lexan here is used for some windows. As you can tell, it's very, very, very hard, and windshields and reusable drinking bottles and DVDs and CDs. So this is the polycarbonate, or the polymer, that's used to make these products here. The polymer industry is a very lucrative industry because, as you can tell, these polymers are used in everyday life. Of course, it presents an environmental challenge because they tend to stick around for years. And of course, as you know from watching the news, that these polymers here are very, very present an environmental challenge. So there's a tight balance that's needed between these polymers and how much is being consumed in society. Okay, this is the end of chapter 19, a fairly short chapter. I hope by now you're seeing that chemistry is not that difficult once you have the basic understanding of the concepts and principles of chemistry. It's just a matter of applying this knowledge and concept to solving different problems. And of course, as I keep saying, that's what we as scientists do. We are problem solvers. So we have the facts, we have the concepts, we have the knowledge, but that's good, but not good enough. As a scientist, we need to be problem solvers. So we need to utilize the skills and the training learned in this course to become better scientists and better problem solvers. So we are almost at the end of the semester. So continue to study hard, and I will post more information on D2L.